Hello there, and welcome to our help video number 1 over our assessment 8-15 on the activity series. This is the first page. On this very first set of questions, what we're dealing with is an activity series where we have nickel as the most active, then tin, then lead, then hydrogen, and copper. Copper's the least active. And they've given us 1, 2, 3, 4. They've given us 5 elements here. And this would be the activity series of metals. Now, hydrogen is included here because hydrogen acts like a metal as it can become a positive ion. All right, here we go. They're giving us 4 reactions. In the first reaction, we have some unknown metal, and that unknown metal is one of these substances right up here. We have an unknown metal, and they've dropped it into a solution of nickel 2 sulfate. Now, when they say a solution of nickel 2 sulfate, that is telling you that it is aqueous and that water is able to pull apart the nickel 2 sulfate. So floating around in that solution, we have nickel ions, nickel 2 plus ions, and we have the sulfate ion floating around. And when our unknown metal is dropped in that solution, no reaction occurs. What that tells us is that the unknown metal is not able to force nickel to take its electrons, meaning that the unknown metal is less active than nickel. So when no reaction occurs, we know that the metal that is in the solution as an ion is more active. So we now know that nickel is more active than our metal. So here's our activity series. We have nickel first. That means that the unknown metal is not nickel. Hydrogen's not a metal, so it's not hydrogen. So we now know that it is either tin, lead, or copper. In reaction 2, the student drops the metal in hydrochloric acid, and a slow reaction occurs, producing fizzing and bubbling. Well, with hydrochloric acid is one of our 6 strongest acids. It dissociates 100%. So when we have hydrochloric acid, we know that there's H plus ions floating around in there. They dropped the metal in there, and a reaction did occur, although it was slow. What that means is that this unknown metal is only slightly stronger than the hydrogen, or slightly more active than hydrogen ions. So a reaction did occur. Our unknown metal is more active than hydrogen. So we now can eliminate copper. We can eliminate hydrogen. It's not even a metal. So now we have that our unknown metal is either lead or tin. We know that the unknown metal is less active than nickel from the first reaction, and we know that it is more active than hydrogen from the second reaction. That means that our unknown metal is either tin or lead. We're guessing it's lead because it was a very slow reaction. The fizzing and bubbling that we saw were the hydrogen gas escaping from the solution as our unknown metal replaced it. In reaction 3, the student waits until reaction 2 is complete. What that means now is in reaction 3, they are going to be using a solution now that now has the unknown metal in it. So in reaction 2, our unknown metal is entering the solution as it's displacing or replacing the hydrogen. So now we are going to drop a piece of tin in this solution that now has our unknown metal. What we see is a reaction happening. So that what we learned from this is that tin must be more active than our unknown metal. Since our unknown metal was an ion floating around in solution, and tin forced its electrons on our unknown metal, causing it to precipitate from solution. So we now know our unknown metal is less active than tin. That means our unknown metal must be lead. This fourth reaction, they dropped a piece of the unknown metal in a solution of lead, and no reaction occurs. Well, that would make great sense. If our unknown metal is lead, lead cannot replace itself in solution, so we know it's lead. We know our unknown metal is lead, and we established that the activity series from our activity series. So based on the activity series above, what is the unknown metal? It's lead. They drop a piece of copper in a solution containing the unknown metal. Would a reaction occur? No, 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 it would not. Copper is less active than our unknown metal, so copper cannot displace or replace our unknown metal, which is lead. In the number 3, a piece of nickel is dropped in a solution of the unknown metal. Would a reaction occur? Absolutely. As we see up here, nickel is more active than our unknown metal. So nickel would displace it. It's more active. Nickel would force its electrons on lead, causing lead to precipitate from solution, because our lead ion would become neutral again as it received the electrons. Water could not hold it in solution, so it would precipitate from solution. And as nickel gets rid of its electrons, it would become a cation, a positive ion, and water would be able to hold it in solution. All right, questions 4 through 6. We're using this activity series right here. The most active is strontium, the least active is hydrogen, and we're supposed to predict the products. In number 1, if we drop a piece of sodium in magnesium sulfate, would a reaction even occur? There's sodium. We dropped it in a solution of magnesium sulfate. Magnesium. Can sodium displace magnesium? Absolutely. So sodium would take magnesium's spot in that formula, and magnesium would precipitate out of that formula, out of solution. And where do we get Na2SO4? We learned that the sulfate ion is 2-. Sodium is an alkali metal, it's 1+. Crisscross your charges. We've got our formula. We've got 2 sodiums there, so we need to put a 2 in front of that. The correct answer, letter D. Number 5, can calcium replace hydrogen, the hydrogen ion, in solution? Absolutely. We actually saw this reaction happen in our lab on single displacement reactions. Wait, did we see that one? Yeah, we did see calcium dropped in there. And what ended up happening here is calcium would replace hydrogen, causing hydrogen gas to fizz. And what would happen here is calcium would take hydrogen's spot. It would replace it, so we would have CaCl2. Where does the 2 come from? Calcium's in the alkaline earth metal family. It is 2+. The chloride is in the halogen family. It's 1-. Crisscross your charges. The 2 from calcium comes down there. We had to put a 2 after the hydrogen, which was displaced or replaced from solution, because hydrogen is part of Brinkelhoff. It's diatomic. It always comes in pairs. So we have a 2 there. We also have a 2 there. So we would need a 2 here. The answer is letter B. In number 6, what's going to happen here in number 6? Will magnesium replace strontium? Well, here's magnesium. Strontium is listed as the most active. Can a less active metal force its electrons onto a more active metal? Remembering that activity with metals, the more active metals are better at losing their electrons. The more active metals are better at becoming cations. No, magnesium cannot replace strontium. We head on down to our final 2 questions, and these are the activity series of the halogens. In our activity series lab, we saw that chlorine was more active than bromine. Bromine's more active than iodine. They did not do fluorine. But if chlorine is more active than bromine, who's more active than iodine, it would make sense that fluorine is the most active. Active halogens mean that they are better at taking electrons. We know that the size of the ions, or the size of the atoms, increases as we move through the family. So fluorine's the smallest, the strongest, it would be the most active. So can chlorine displace bromine? Absolutely. We actually saw that in our 8-13 lab on the activity series. So what happens here is chlorine will replace the bromine. A nonmetal replaces the nonmetal. So now chlorine is with the potassium. Up here, metals replace metals. Down here, nonmetals replace nonmetals. So chlorine's there. Why isn't the 2 next to the chlorine? We have a 2 here. Why don't we have the 2 here? Well, that is because this is a compound. We get the charges of the compound by crisscrossing. Potassium's 1 plus, chloride's 1 minus, crisscross. This 2 here is because chlorine is a diatomic element when it's by itself. It's the Cl in Brinkelhoff. One chlorine can share with another chlorine to become stable. Here, chlorine's not with the chlorine, it's with the potassium. Why do we have the 2 here? Because bromine is the Br in Brinkelhoff. It is a diatomic halogen as well. One bromine is going to share with another bromine because they each need one. They share, they can satisfy the octet rule. So we have 2 bromines here. We have 2 chlorines here. There should be a 2 in front of this in the balanced reaction. There should also be a 2 in front of this in the balanced reaction. There is no 2 here. Whoever did this is foolish. There should be a 2 here. There should be a 2 here. So the correct answer is letter D. Can iodine replace fluorine in solution? In other words, can iodine strip electrons off an F minus? Absolutely not. Fluorine's the most active of the halogens. Iodine's least active. A big, large iodine cannot rip electrons off a small, tiny fluorine. That is no reaction. Hopefully this video helped. If this video did not help you and you have additional questions, don't hesitate to email your question. We can set up a meet to discuss any of the questions you might have on this handout. And good luck.